we take a look at conjugate functions. So the conjugate function is defined as f star of y equal to max over x belonging to domain of f, inner product of y comma x minus f of x. So that is the definition of the conjugate function. Observe that the objective function in this maximization problem is affine in y, right? So it is affine in y, and we are taking a pointwise maximum of an affine functions in y, and therefore the conjugate function is always convex, because pointwise maximum of affine is always a convex function. So this is always convex. Note that an implication of this definition is that f star of y is greater than equal to y comma x inner product minus f of x for all x, because this is the maximum. So the maximum is always greater than equal to y comma x minus f of x for a given x, for any x. And in other words, you could say that f of x plus f star of y is less than equal to inner product of x comma y, right? So this is an interesting implication of the way in which conjugate is defined. Let's take a simple example. Let's take the example of f of x equal to half of x transpose x, right? Or half of norm square of x, where x is a vector. In that case, the inner product is simply x transpose y. So what is the conjugate? You can see that the conjugate in that case is given by max over x y transpose x minus half of x transpose x, and of course we can simply calculate the maximum here by differentiating. So we will get y equal to x, which would imply that this objective function, the maximum value will be equal to half of y transpose y. So in other words, the conjugate of the function x transpose half of x transpose x is that function itself, because y here is a dummy variable. And in fact, the inequality that we have seen so far, x transpose y is less than equal to x transpose x by 2 plus y transpose y by 2. So this is a general inequality that follows from this result. So this is an example, and in fact a special case, where half of x transpose x is the function and its conjugate is the function itself. That is not obviously always the case. There are scenarios where the conjugate is not the function itself. Let's take a more complicated example. So let's consider f of x equal to norm of x, right? So this is the L2 norm of the vector x. Let's calculate f star of y as max over x transpose y minus norm of x. So how do we solve this? To get an intuition as to what is going on here, it might be beneficial to first consider the n is equal to 1 case. Of course, we want to solve this for the general n, but it might be very enlightening for us to first consider the n equal to 1 case and see what is going on, and then proceed to solve it for the general case. So let's first consider n equal to 1 case. So in case we are talking about a special scenario, we have max over x is a scalar now, and we are saying that max over x, xy minus absolute value of x. So norm of x is the absolute value of x for the scalar case. To do this, let us consider the two components separately and then plot them. So what we will observe is that absolute value of x, or minus absolute value of x, looks something like this, and xy would basically be a line which would look something like this. So this is xy and this is minus absolute value of x. Of course, this is xy for the case when y is positive and if y is negative, then xy would look something like this. So this is the case when y is negative. Right? So what is the sum of these two? Here, of course, there are two scenarios. So case 1 is when the sum of these is always negative, and the case 2 is when sometimes the sum could be positive. So the case 1 actually occurs, you can see here that the case 1 occurs when y is small. If y is small, what would happen? If y is positive and small, then the sum of these two would look something like this. So this is xy minus absolute value of x, and this is the x-axis, and this is y small positive. In the case when y is small negative, it would also look something like this. So this is y small negative. In fact, you can see that for it to be small, y has to be less than 1. So this case really is that absolute value of y is less than 1. And in both cases, you can observe that the maximum is at 0. Right? So if y, absolute value of y is less than 1, then the maximum is 0. So let us go back and write this as 0 whenever absolute value of y is less than equal to 1. And what happens when absolute value of y is greater than equal to 1? So in that case, you can observe that it would add up to be something like this. So this is the case when y is large positive. And similarly, when y is large negative, then it would look something like this. So this is again xy minus absolute value of x, and this is the x-axis, and you can see that in both the cases the maximum is actually at infinity. So the function value increases to infinity in both the cases. So going back, we obtain that this is infinity when absolute value of y is greater than 1. So this is the solution of the n equal to 1 case. And we can expect that in general n case also it would look similar, except that the absolute value would be replaced with norm, which is the measure of the length of a vector in general case. So in that case, we would have to consider therefore two scenarios, one in which norm of y is less than 1 and the other in which norm of y is greater than 1. So let's consider the general case now. So let us consider the general n case now. So in the general case, again we have two cases, one in which norm of y is less than equal to 1. If norm of y is less than equal to 1, remember that we had the inequality x transpose y less than equal to norm of x, norm of y. So this is the Cauchy-Schwarz inequality, right? This is the Cauchy-Schwarz inequality, and we can subtract norm of x from both sides. So we would obtain norm of x, norm of y minus norm of x, which can be written as norm of x times norm of y minus 1. Now this is interesting because norm of y is less than equal to 1, and therefore you can see that this quantity is always negative or non-positive. In other words, this is less than equal to 0. Now we are saying that the objective function is always less than equal to 0. In other words, the maximum of the objective function over all x is always also less than equal to 0, because this objective function itself is always less than equal to 0 for all x comma y. Therefore the maximum is also always less than equal to 0. In fact, in this case we can see that the maximum is equal to 0, which occurs when x is equal to 0. So this inequality becomes an equality when x equal to 0. So in other words, the maximum of this is equal to 0 and it is attained at x equal to 0. In other words, we can conclude that f star of y for f of x equal to norm of x is equal to 0 when norm of y is less than equal to 1. So that was the case 1. Let's also look at case 2, which is that norm of y is greater than equal to 1. Now in this case, actually the problem becomes unbounded above, as was happening for n equal to 1 case. And we can show this by observing that our objective function x transpose y minus norm of x can be written as, so what we can do is we can try to see which direction I should increase x, or which direction I should take x so as to make this infinity. So that direction actually turns out to be alpha times y by norm of y. So if we substitute x equal to this particular value where alpha is still could be anything, we obtain alpha times y transpose y divided by norm of y minus absolute value of alpha, or this can be written as alpha times norm of y minus 1. Now norm of y is greater than or equal to 1, so this quantity is positive, and therefore this quantity would go to infinity as alpha tends to infinity. In other words, if I take x in this direction and for a large alpha, then the objective function can be made arbitrarily large by choosing the appropriate alpha. In other words, the objective function is, the maximum is unbounded above, and therefore the conjugate function is equal to infinity when norm of y is greater than or equal to 1. So to summarize, we have seen that for fx equal to norm of x, the conjugate function is 0 when norm of y is less than or equal to 1, and infinity when norm of y is greater than 1. So it should be greater than, not greater than equal to. And you can also say this as the domain of f star of y is the set of all y such that norm of y is less than or equal to 1. Because remember, domain of a function, of a convex function, is defined as the set of all arguments where the function takes a finite value, it does not take an infinite value. So that is all about the conjugate functions and the examples.